Hello everyone. Let's solve the Leetcode problem. Find a path exists in graph. The question number 1971. There's a bidirectional graph with n vertices where each vertex is labeled from 0 to n minus 1. The edges in the graph are represented as a two-dimensional integer array uh, where each edge is denoted by ui and bi. It's a bidirectional edge between vertex ui and bi. Each vertex pair is connected by at most one edge. So that basically means there is no, there is no, there are no two edges between nodes. It's only one edge, and no vertex has edge to itself. So no node is connected to itself like a loop. So the loops don't exist, and between two vertices, only one edge exists. Given edges and integers n source and destination, return true if the valid path from source to destination, or false otherwise. So basically, if they've given basically the number of nodes, they've given the edges as a list, and then you have source and you have destination. From the look of it, you can make out, you can go from 0 to 1, 1 to 2, you can go directly here. So from the look of it, you can say that this ought to be true, right? You can go from 0 to 1. It's a bidirectional graph anyway, so this is sort of obvious. What about the second example? Right, there are six basic nodes. There are about 5 edges, and the source is 0 and the destination is 5, right? So this is obviously false. There is no line connecting 0 to 5 unless you can figure out a way, unless there is an edge from 2 to 4. So obviously this has to be false. Now how do we solve this? We solve it by basically DFS or BFS, right? So DFS would be, so you have a node and then you maintain another set every time you. So the reason, if you apply DFS onto node 0, which is the source, you go to the neighboring node, and then you immediately go back to, as part of the DFS, you immediately go back to 0. To avoid that, we maintain a set which has entries of all the visited vertices. That ensures that you don't go back to 0 and that you don't count it again. And then you go to 2, and then you add to the list. Right? So that's the end of DFS, because there is no way you can go from 2 to 4. And then if the set doesn't have, let's say, the destination, if the set has to have both source and destination, it only has the source, doesn't have destination, so you return false, right? So if you do BFS, it's still pretty much the same, unless there is an edge connecting 3 and 4. Then that's a edge connecting 2 and 4, sorry. So if there is an edge that is added, then obviously the way you end up solving this is to implement DFS, and you go from 0 to 1, and then you note it down. You note down in the set that you going from 0 to 1. Then you end there, and then you go to 0 to 2, and then you go from 2 to 4, and then you go to 3, and you go to 5. And since the source and destination are both available in the set, you return it as true. If you can do the same, I mean, this becomes sort of obvious here, wherein you do the same version. You do DFS first, and basically you start with source node 0. You go to 1. Every time you visit a new node, you add to the set. You don't, as a result, which this prevents you getting into an infinite loop here. Then you go to node 7. Then you end here. So if then it will look at the corresponding node 2, and then it will add to the set, and then instead of going back, it will look at 6. Again, it will end here. So if you're doing, let's just say, this is again false. How do you do it if you're doing BFS? Basically, you go to 1, you note down 0, 1, and then you do 2, then you do 7, then you do 6, right? And let's suppose in the same way, if these two are connected, 6 and 4 are connected, somewhere, that basically means these two are connected. So if these two are connected, then obviously you go to 6 and then you go to 4. If you're doing, you go to 4 and then go to 3 and you go to 5 if you're doing BFS. If you're going DFS, you go to 3 first and then you eventually go to 5. And then you add these sets, these nodes into the set. And since source and destination are both part of the set, you basically say it's true. That means these nodes are connected. So you understood the logic, right? So now we have to code this up. So basically we are coding up a valid path. So we open up a file. This is like the general class that we start with any solution. The name of the function is, name of the method is valid path. We have integer, we have edges listed as list. Source and destination. So first thing that we will check, before that, the input that we have to take, the input here is basically we have number of nodes, you have edges, you have source, and you have destination. You have two alternatives for edges that we sort of two alternative for edges. So I'm assuming the audio is getting recorded. So first thing that we will check, before this, we have to add some import statements here to import some libraries. We have to import list. We have to import default dictionary that we will end up using for graphs. So the first condition that we check is if the source itself is the destination, then we basically return true, right? And then we assign default dictionary with list as parameter to graph. Then we look for, we basically append nodes of the graph to each other, and you can run it through a for loop. And since it's bidirectional, I mean, it's not just one way. You can, the graph is bidirectional. We have to ensure that the nodes connect the other way as well, right? And this has the worst case scenario wherein this can get into a loop, as a result of which we will have some sort of a hash set we can basically declare this as source. This scene is basically a set which stores all the nodes that we have visited. So we can do it this way, or we can just declare it as set, and then we can say scene add source. So you added the source vertex source node for the scene set. Then now you basically write the DFS depth. I mean, I've been saying DFS throughout. DFS is depth first search, and basically you look at the condition that if I itself is destination, then you return true again. If not, you look for neighbors in graph, and basically look for, as we described in the previous process, as to how to look for nodes in the neighborhood. Where this NEI is basically talking about the neighborhood, and we're looking at neighborhoods, and then we check if neighborhood is not already in scene. Scene is basically a set which stores all the visited nodes, and you're basically accommodating or accounting for the case where the node is not in scene. If the node is not in scene, you might as well add it in scene by saying that you add the neighbor or the visited node in scene. And then this depth first search is also a recursive algorithm as opposed to breadth first search, which is more of an iterative algorithm. So you call DFS again here. If it is true, return true again. And then if not, you return false. Then eventually so you're having three recursion statements here, wherein you're calling the DFS function three times, the main function statement, and in that you're writing it here, and once you get out of it, you call this again. Okay, this code will work, and let's see. Let's run this and check. Before that, since we are executing this not an Leetcode platform, and then basically in VS Code, we have to essentially initiate the constructor and assign that constructor to a reference point, and then this reference point can invoke the main function that we have written, and then we have to pass the input as parameters, right? And then it's a good idea to assign this to result and then print this at the end so that you can see the output. We haven't stored the file. Okay, then there are some errors. As you can see it's giving an output as false. That's because, as you can see, there is no connecting. So 0, 1, 2 are part of one tree, and then that is not connected to 3, 5, 4. But let's check the other case, just so that we can be sure that this works. We can give this as input, and then run this again. This ought to be true, which is the right thing to do, right thing for the program to be giving as output. So if you have any questions, do let me know. That's how you implement valid path exists in a graph using DFS using recursion. Thank you.